Right, okay, I'm gonna just talk about the hopefully final version of my rendering system. For me, it's Pac Dizzy. But just to explain what the rendering system's got to do. So you're drawing these isometric um, scenes, and what you want to do is you want to draw from back to front, so that the last things you put into the scene overwrite things that are at the back. Now, on standard bitmap based graphics devices, this is easy because you work out what pixels to write, and you have like transparent pixels, so you don't write pixels that are marked as transparent. But on Pac-Man hardware, the tile map is not bitmap based, it is tile based. So what you do is you have a cell, and I'll just show you, I'm running it in main. You have a cell, and each one of these is a cell. Let's just zoom them. I'll zoom them in so you can see them better. Each one of these is 8 by 8 pixels, and you have a number associated, so you can see the one in the top left hand corner is tile 0, the one at the right is tile 8, etc., etc. And you have a small amount of RAM that's dedicated to the tile map, and you just put in the number of the tile you want to appear in a certain location. So the screen's built up by these 8 by 8 blocks, and they're fixed. You can't edit them. They're in ROM, so you can't do any jiggery pokery. You can't look at the pixels in there or anything. All you can do is you can put them into the scene. So what you've got to do, because there's no transparency, there's only one layer for the tile map. So you want to be able to put one tile on top of another and have a combined image, but we can't do that. So what we've got to do is whenever we're writing a tile to the scene, we need to look at what tile's already in the scene at that location, and then what the renderer's got to do is it's then got to look up to see if I've defined, and I've had to do these all manually, if I've defined any what I'm calling a compound tile. So a tile that makes it look like that one tile's on top of another. So if you look down at these at the bottom, you can see that some of these don't look like normal shapes because they're there to represent a background tile with a foreground tile on top. Okay, so you can see this one here. I don't know whether you can see the cursor actually. So if you look at the one above the 2, that's obviously got some diagonal shape in the background and then something going straight down, probably a ramp tile, that what foreground one is. So what we do for every single tile that we draw, we have to check to see if there's a compound tile. So this is a massive search algorithm. Okay. Now when I did my first version of this, I just dumped all the data and did a linear search. So if you look on the right hand side of the screen, this is what the data looks like. Effectively, it consists of 3 pieces of information. So there is the first number. So if you look just below the 2015 bit, in the middle of the screen at the top, we've got 0, 0, 8, 91. So what that shows is if we've got tile 0 on the screen currently, and we want to put tile 8, then what we need to do is actually write tile 91. Now you'll also see that there's only 2 compound tiles for 0. So there's only actually 2 tiles that are ever, in the way I've got the data set up, only ever written on top of tile 0. So actually it's a more complicated search problem. You've actually got to search to see if something's there or not. Okay, so I did a linear search. So I laid all this data out just in consecutive memory locations. So it went 0, 0, 8, 91. And all these, so it takes up about 930 bytes. And my first version of the renderer just started at the start and ran all the way through. So if you were looking for the very last tile, which is tile 218, and you want to put a 2 on there, you'd have to look at all these other tiles. So it's a bit cack. Linear search is the name of that type of search. It is not designed to work with large data sets. It's very quick if you've only got a few. you know, like 10, 12, 13, something like that. That's it, quick. Now, I'm not talking about modern processors where you've got cache and you can take advantage of level one cache and all that crap, because that's a different ball game. But on these old school processors, they didn't have cache. Okay, so everything was a read from memory. So you want to try and minimize the amount of that you're doing and the amount of comparisons you're doing. Okay, so what I've done is I spent quite a deal of time thinking about how I could reorganize this data to allow different search methods to be used. Okay, so what I ended up doing was writing, and you can see these different color sets. They're the different sets of tiles. There's 94 different ones. What I've done is I've writ loads of individual linear arrays, which is just lists, that contain the tile we want to place and the compound tile, so pairs of tiles. Okay. So what I've devolved the problem into is that once I've found the current tile, the existing tile in the tile map, if I look at its array of compound tiles, that becomes a trivial linear search that's quite quick because most of these are small. In fact, some of them have only got like one or two. There's a couple that have got like 16, but it becomes a more manageable uh, search job. Okay, there's no point in implementing complicated search methods on that because the time taken to implement that and the time taken to execute, you're not going to get any benefit. So a linear search for that bit. So there becomes another problem that we need to solve. We need to find which address the array for the existing tile starts. So if I'm looking for tile 26, that's going to be the compound pairs for tile 26 are going to be somewhere in memory, but I need to know where in memory they are. So I have to still do a search so that I can look up an address. So I built three different methods. Okay, so we've got the standard one, which is the one that's being used at the minute. So if I just get this to change view, you'll see the rendering. So this is you can see it's quite slow. This is the linear search method, but I have implemented three other methods, and I've made them all like interactive in this. I don't want them all. They take up tons of memory, but I've implemented three. So if I just press the up key, right. So the first way I thought of doing it was to organize the background tiles. That's the first number in the compound lists into a tree structure. So I search a tree structure. Now tree structures are good because you can binary search them. So you look at the first item in a tree and then you can discard half the tree every time you look at an item. Okay, a little bit complicated. You've got to follow pointers. Now in this, my pointers, I didn't want 16-bit pointers because that takes up loads of memory because you have to store all these pointers. So I wanted 1 byte pointers, which was a little bit of a problem. So I had to like take the tree and I had to write more code. I did all this in C Sharp, but I wrote more code to reorganize the tree so that the branches weren't more than 255 bytes long. All right, because the tree is actually 470 bytes, so some of the branches could have been. Um, so that was a bit of complication. I tried doing a depth first search of the tree and a breadth first, and there was issues with the depth one, so I used the breadth one. That managed to give me branches that were short enough to fit in a byte. Well, they were offsets, not branches. So, so that's that method. And you can see when I flick through the views, it's actually a lot quicker than the linear method. Okay, this scene from that angle isn't very complicated. There's a few overlapping tiles, but not too many. You can see that it slows down when it comes round because there's more overlapping tiles there. So there's more searching of the compound tiles. So that was that one. It uses quite a lot of memory. It's the most expensive one. It uses about 1200 bytes just for the data. Okay, so that's quite an expensive one, but it's quite a good technical exercise. It turned out not to be the fastest of the methods that I used, but hey, that's what it is. Right, so I did that one and I was like, okay. So I thought about another one. So built an index again. So all it consists of is the tile that's currently in the scene and an address of where the compound tiles for that tile exist. So 3 bytes for each one of these. Now, what I do with this, I've just got an array. If you've got an array in order, the best search technique that you can use on it, because arrays are nice for this, is binary search. So this is like a tree search, but it operates on a linear list. Okay, so they have to be in order. So you have to start with tile 0 at the start and then go tile 1, tile 2, tile 3. But it allows you to search. So the way that binary search works, you just look for the middle item, um, see if that's the one you want. If it isn't the one you want, and because they're in ascending order, you know that all the tiles to the right of that, all the items in the right of that, they are going to be bigger. So you don't even need to look at them. You say, well, we'll just ignore that. So you throw away half the data. So you just like keep finding a middle point in the rest of the list that you've got left. Okay. So it's super quick. In fact, just to give you an idea of how quick binary search can be, if you've got a million data items to search and you're looking for something that doesn't exist, in a linear search, you'd have to look at a million items. In a binary search, you can actually identify that something doesn't exist in a list by just looking at 22 values. So out of a million, you look at 22 because you're doing this discarding. So binary search is so awesome. It's really useful if you've got data in a linear um, list, which I managed to organize for this. So let's see how quick that one is. So you can see that that one's quick. It looks about the same sort of speed as the tree, and to be fair, it's in the same order as the tree because the tree is a binary search as well, but in a more complex data structure. Okay, it doesn't have to be linear a tree, which is quite nice. Um, so yeah, you've got two methods that do divide and conquer search methods, which is what binary search is. The the linear binary search method, it uses a little less memory. Okay, so that's obviously preferred over. The code's a little bit more complicated to do that because you're having to like calculate mid values, and that's like, oh, especially as they go over a byte again, so you can't use you have to start messing about and like multiplying up and all sorts of weird things while you're doing that. But it it operates about the same speed. I would say that the tree version's slightly quicker with more complicated scenes. Not done exhaustive testing, but I did some testing on that. Okay, so I went. I was happy with that, but then I thought, hang on a minute. If the tree's using 470 bytes to store its tree, um, I actually can do a lookup table that is quicker than that. I've only got 219 or maximum 219 tiles that may have a compound. So what I can do is a lookup address. So if I know some of them don't have them at all. So if you look at these numbers, you can see that there is no 12, 13, 15 or anything like that. Now I can't make a sparse array, which is the way you do it in a high level language with loads of memory. So I have actually got to have lots of waste on this. So all I do is I have a set of consecutive addresses that have the address of the compound tile lists for each block. Okay, and there isn't any calculation other than doubling the tile number. That gives you an offset into this lookup list. You add the start address of where the list is in memory, and then you just load up the address and you go. So there's a little minor calculation to do, a doubling and an adding, and then you've got your address and you go off to that address and you can linear search. Okay, so I implemented this. It uses less bytes than the tree. So it's a bit of a no-brainer. It's quicker than the tree because it's not doing a load of work following a tree structure, and it uses less bytes. So this is the one. So if I just, this is the one I'm going to use. So I'll just show you this. So this is the lookup table method. So you can see it is significantly faster. Okay, now this, like I said, this isn't a complicated scene. I'll go to the next map in a minute and I'll run through a few other ones as well, just to show you how ridiculously quick it can get. But what I've done is I've unlocked the view changer so that it will run as fast as it can. So if I just hold down 2, you can see how quick I'm flicking through. If you look at the arrow, you can see how quick it's going round and rendering. Okay, so if it's back on north, let's go back to the original one. Yeah, it does that, crashes sometimes. I thought I'd fix that. It doesn't matter. I'm not bothered. It's Stack Overflowing or something. I don't know what I've buggered something up. But if I run this one as fast as I can, you can see it's absolutely awful. Really slow. Let's go back through the other ones. Let's do the tree. You see the tree's quite quick. Watch the arrow. That's the good indicator. The binary search one, slower than the tree. You can see that from looking at the arrow. But when you get to the lookup table one, it's significantly faster. Okay, so let's go back to the slow one and we'll move to a different scene. Right, now this looks like a simple scene, but actually every tile you draw is in front of another tile. So it's really heavy duty, this one. So let's just flick, I'll run this at maximum speed. So this is the original one. You can see, you can actually see the individual tiles being drawn nearly. It's so slow because it's having to do so much searching. Let's have a look at the tree one. Let's move over to tree. You can see I've got a couple of artifacts there because I think I cocked up part of the tree implementation. And I'm not going to bother looking at it. But you can see that that's significantly faster. You still see it being drawn, but it's significantly faster than the other method. There's the binary search or the linear list. Yeah, about comparable with a tree. And then the lookup system, well, it's a no-brainer. Okay. So that's the one I'm going to favour. Let's go to some different scenes. So this is a simple one. There's some overlaps, but you can see how fast that's rendering now. I could nearly do animations, and this is quite a simple one. So that's rendering quite quick. That's quite a simple one. This is a complicated one, but it's actually there's not that much overlap, so it runs actually quite fast. That was just a stupid test one to test some overlap stuff. Go back to that one. This one, not much overlaps. If you look, there's not much. Remember, everything's square, so you can't have triangles and things. But yeah, that one renders quite quick. Here's a quite nice one. That renders quite quick. I was quite impressed with how quick that one did. And that one renders quite quick. And then this is one that you'd think would render really slow, but actually it's really quite fast. So that's the render system. I think I'm not going to do any more work on the render system. I've got to now rip out all the testing code and the other methods out. See how much memory I've got. I'm using about 1200 bytes in total, including the code that does the searching. So with the render, I'm using about 2K. I've got 16K in total. I'm using 2K just for the rendering. So I've got quite a bit to play, but don't know how many rooms I'm going to be able to make. I've got to look at some compression code to try and squeeze more rooms in. But my next bit is to get the movement going, and then I've got to do collision detection, which is not going to be trivial because I've got slopes to worry about. So I've got to get the movement, the acceleration, the deceleration, get that balanced. Then I'll have a look at the collision detection, and then I can actually start trying to make it into a game. So a moderately simple bit for the movement, and then a horrendously complicated bit for the collision detection. And then the final job is to do the occlusion. So to draw on top of the character, Gerald, when he's behind something. So that'll be a barrel of laughs as well. But I've sort of already worked that out in my head how I'm going to do that. It's just a matter of sitting down and doing it for real and seeing that my ideas are rubbish and starting again, which is generally how this works when you're programming. You have an idea, you think it's a great idea, you implement it, it's absolute kibosh, and then that actually leads to ideas popping in your head that help you solve it. Anyway, I found that interesting. I probably just bored everybody to death, but there you go. Thanks for listening.